Hey everyone, so this is the second part in a series on deep learning using ArcGIS Pro. Now, if you haven't watched the first video in this series, it'll help to explain a lot of the concepts I'll go over in this video because it deals with a lot of the basics, so creating your training data samples, uh, exporting these training data to the correct format for ArcGIS Pro to use, and then also training the very basics of training a deep learning model in ArcGIS Pro. And so in this video, I'll be going over an optimization strategies for deep learning in ArcGIS Pro. Now, before I get started, I'll just go over the dataset I'm using today. So this is different from the one I used in the previous video. Now, in this video, I'll be using some planescope imagery. So this imagery is from a company called Planet, and this here is an image that I've cropped to the boundaries of a municipality in Ontario, Canada. And so it has a mixture of agricultural land, a lot of suburban areas, some industrial and urban areas, as well as highways, farms. So this is just an example data set that I've created over top of it using the training samples manager. And I've already gone ahead and ran export training data for deep learning. And so the Planescope imagery is captured by a constellation of satellites called Dove satellites. They look like the satellite here on the right. So this one is 10 centimeters by 10 centimeters at the base, and then the length is 30 centimeters. So they're quite small and compact units. And each time they launch them, they can launch many of them into space at once. And so the entire constellation of these little satellites can capture basically the entire planet every day at 3-meter spatial resolution. So I just selected to use imagery with 4 bands, but they have imagery now with many more bands than this. And some of them are interoperable with Sentinel-2, so they share the same radiometric wavelengths that Sentinel-2 does, or they've been aligned in software to Sentinel-2 bands. So this makes it easy if we want to work with Sentinel-2 imagery as well. But in this case, we won't be going over any of that. We'll just be sticking with the imagery that has come pre-calibrated for us. And so I mentioned the classification already, and it has these 4 classes, so highways, industrial and urban areas, green spaces and agricultural, and then suburban areas. And so I know some people would separate industrial, urban, and green spaces and agricultural, but to make it easier for myself to create this data set, I just mix them together. So if you were using this as an example, you could separate into many different classes. And so just heading back to our ArcGIS Pro, we can then go and we see that they actually have a tool using AutoML for machine learning and AutoDL, so automated deep learning. So this tool would run through a pre-defined optimization and deep learning basically workflow that they've created. And so one disadvantage I found of this is that it takes a long time and uses a lot of video memory. So for a lot of people, this might not be a very realistic option. So what we can do is we can use Python programming in ArcGIS Pro to create our own optimization and model selection routine that hopefully will be a lot quicker and maybe more efficient than the one they have there. And so in the future, we can always compare this, but for this video, I'll be going over the routine that we'll create. So just heading back to the presentation here. So there are really 2 main or very basic optimization schemes that are being used. So the first one is independent optimization, and in that scheme, the future trials, so the parameters that future trials use are not linked to any way to the past trials that have already been run by the optimization algorithm. And the second way is sequential, or also known as adaptive hyperparameter optimization. And so future parameter selections are informed, related, or dependent in some way on existing trials. And so we can look at two very popular algorithms for each category, so random search and tree structured parse and estimators. So just starting off on the left, so in the paper Random Search for Hyperparameter Optimization in 2012, they found that random search was much more efficient than grid search and manual searching for parameter optimization combinations. So, really, the goal or this baseline standard that many adaptive algorithms are compared against is random search. So, if your algorithm is faster, more efficient than random search, then you've likely created an algorithm with some worth. And so I know it's a bit of a simplification of it, but if you want more information, I really recommend that you read each of these three papers, as they really go over on the left uh, the benefit of random search over grid searching, and the papers on the right here really go over the benefits of sequential parameter optimization over just basic random search. Now, random search has the benefit of being very easy to set up and very simple for someone to understand, and it usually can find the parameter combination that lies close to the optimal combination, whereas the tree structured powers and estimators basically use probability distributions to locate and to sequentially over time adjust to the parameters that will create the optimal combination. Now, the benefit of tree section powers and estimators is we can use these in many optimization frameworks. So it's supported by both Optuna and Raytune. But luckily for us, Optuna is actually included with the deep learning tools that you have to install with ArcGIS Pro, so we don't have to go and modify our Python installation anymore after we've installed the Esri packages. And so really these frameworks require you to create three main steps. So that's actually defining an objective. So what you actually want to optimize and the parameters you want to select. And then two, you actually set up your search space. So what combinations, or in our case as well, what models we want to select. And then the third step, you really just set up the framework and then run it. And so we can use this three-step process, so defining your objective and then searching and then setting up the framework can optimize basically anything that returns accuracy, error, intersect over union, or any other any other function with some sort of objective linked to each trial. So I'll be using the Esri developer Python API, but you could accomplish something similar using the trained deep learning model and the standard ArcGIS Pro coding. I just find that for this purpose, it's a bit easier for us to follow the coding of the ArcGIS Enterprise API. So I'll just go back and switch to ArcGIS Pro and we'll continue with the actual coding tutorial. Okay, so now that we're back in ArcGIS Pro, we can see that I've already exported my training data set using the tool I went over in the last video. And so we don't need these samples anymore, so we can actually switch to our Python notebook. So to get there, you go to Analysis, then Python, and Python Notebook. So that'll open basically a Jupyter Notebook within ArcGIS Pro. So to start off with, we have to really just import our training data and set some just some settings. So for ArcGIS, we can set our seed. So the chip size that I selected was 256. So I'll just define that here, and then I'll set my validation split percentage. So I'll be using a 20% validation split. So with the number of epochs, so the number of times that the data is ran forwards and backwards through the model, is going to be set at 20. Now this is just for me to save some time when running this, but usually you'd set it higher than 20 and you would turn on early stopping. So what that'll do is it'll stop training once there's no longer meaningful improvement in our case accuracy. And so for batch size, so your data is loaded onto your GPU in batches, but since my GPU is a very small video memory, I'll set the batch size to only 3. And so now we define our the location or the folder for our training data. So for me, that's on my D drive. And the municipality is called Oakville, if you were curious. v2 slash. Okay, so now if we're using the ArcGIS Learn API, we have to set something called prepare data equals. So here I'll just go ahead and copy the training data folder. So I think this we're going to call chip size, and I'll just set that to chip size I have here. So I think we need split percentage, and then batch size. And so our next one is called imagery type, and so in my case I'm using image with 4 bands, so that's multispectral instead of just RGB, so I have to input that here so it knows the correct type. So this shouldn't take you very long at all to run this command. Okay, so it looks like I remembered all those parameters properly. So now we can go ahead where we will set our actual training or optimization workflow. So in this case, we'll have to import Optuna, and from Optuna, we'll import the optimization algorithm. So in that case, I'll be using the tree person estimators. So if you wanted to, you could use other samplers available in Optuna. So if you wanted, you could just use random search as well. So first we define our objective. And so within the brackets here, I'll put something called trial. So this will store basically the suggestions that it'll later report to you once you've finished running through the optimization routine. So first of all, we can start with model selection. So there are many models available by default within ArcGIS Pro. And so I'll just use a few of them here that I know that should definitely work with this classification data set. So the one I've shown at the start of this video. And so I'll create something called nModel, and I would use the trial dot. So in this case, I'll be doing suggest categorical. And so if you were, for example, using suggest integers or suggest float, then you would use those two for integer and float values. So for example, if you were trying to optimize, say, the depth in random forest, you could put suggest int and then 1, 5, 10, 20, and different whatever values you wanted. And so for this one, I'll just select, you have to say what this is. So model, because this will help you to understand what this parameter is once it reports it to you at the end. And so model, I can do a very popular one. So unit, and then I could do PSP. Net is, I think, another one. That should work. And then we could do so I'm just going to go through like 4 of them that I know. That should work. And then Deep Lab. They're also more popular frameworks. Sorry, popular models. So closing bracket. And so to actually use each of these models, we can create an if statement. If n model equals unit. I'll just copy this. So if n model equals this, so that in here we would say we would actually run and specify the model. Dot learn dot unit classifier, and in here you would set your model settings. So pro, we would take our process data variable here and copy it back into there. And so you can also choose to optimize the model backbone using this routine. You would put another variable down there, and in the trial you would just suggest a categorical, and you could use different backbones that are available for your models. In this case, I'm going to use Resonate 18, so it doesn't crash while I'm running the recording, because Resonate 18 uses a lower amount of video memory. So there you go. So in this case, so far we have it set up so it could select UNet as one of the possible models to test. And so next we can go for PSPNet. So we would do elif n model equals PSPNet. And so instead of starting off with the model, we could start off with some parameters we want to optimize for this model as well. So we could do one parameter I know. So in this case, it would be to use the point rend model within PSPNet as well. So we could just create point rend true or false. And so we'd create trial dot suggest categorical. So in this case, we could call it something simple. We can just call it point rend. And this could have two options, so true and false. And so now we would actually define our model. So I'm not going to type that out again. So we need the same process data, and we would need the same backbone. But after that, we'll also need the option for our trial there. So we would put point rend, and then we can copy this. So we've set up the model as well as a parameter example we can optimize for that model. So you'd want to go through the model options available for you for what type of classification you're running or deep learning goal you're trying to do, and then for each one you could go and then look for different parameters that they have made available for us to change. And some have a lot of parameters, some might not have many settings you could optimize. So we'll go on to the next one, so we can go MMM. And I think this, so we can create a different parameter for this one if we want to optimize that. So MMM can use different models. I'll call that MMS models. And so within here, we will specify different models that I think will work. So we try FCN, fast, CNN should work. And then I think there's one called CGNet. Okay, so now we actually define our model here. And so here we'll stick with our process data and the same backbone. I know you could optimize that here if you wanted, but now we just type in our model. So that would equal one of these possible models. And so that's it for that. And now we only have one option remaining, so we just have to type else. And no, that would just lead us to DeepNet, to DeepLab, because we've already specified UNet, PSP, and MM. So this is all that's left. And so I think DeepLab has this setting, so I'll just copy this. So we can use this for DeepLab. And so it uses the same as this. Okay, so now we have actually defined all our models, the possible some settings for each model we can optimize, as well as selecting between different models. So finally we have to create our fit. So model.fit. And so we'll take up here our remaining settings, number of epochs, then so for learning rate, I'm gonna set this as none. So this, I'm actually suggest an optimal learning rate that it finds for each of these models every time you run it, just to make it easy for myself. And then early, I'll turn on early stopping like I talked about earlier. So this will stop if it isn't improving anymore. And so finally I talked about that we have to report some sort of metric for each trial that we're going to optimize. So in this case, I'll just return accuracy. So this would just be model dot. So this will just return your final accuracy after it runs model.fit. And so now we've created our objective function. So we're on the third step. And we just have to actually create our study object and optimize, and basically run to optimize our objective function. So here we'll just call it study, and then dot, and it's really simple. It's just create study. And so important thing is direction. So in this case, for accuracy, a better accuracy is what we're trying to achieve here. So here for direction, we would put maximize. So you always want to make sure that you're maximizing accuracy. And if it's another parameter you might want to minimize, then you would change this to minimize. And I always define it just so I know and see every time, as well as the sampler. So in this case, we're just going to use the TPE sampler. You can choose this sampler or any other one you like, but personally, I try to lean towards samplers that have some sort of dependence or relationship to previous studies, because I think that's a more efficient way to do it. And so we go study.op optimize. So this should actually run our optimization routine with that study we've just created. So now we'll put in our objective here, and then the number of trials. So for TPE, usually you would run anywhere from 100 to 1,000 trials, and this depends a bit about the number of parameters you've selected, but if you have like at least 5 parameters, in this case they're all categorical, but normally if they were suggest float or suggest int, then the trials would be higher. So for this example, I'll set to 12 just because we only have a small number of possible parameters here, and I don't want to wait all day for this to finish. So normally if you could also suggest parameters, and so you may start at something like 200 or 100, but if you were getting started, you didn't have a clear idea of what would be optimal already, then you would likely start closer to 1,000. But in this case, we'll just start at 12 because I'm going to save some time here. So I'm going to run this, then I'll come back and finish the video once it's finished. Oh, so I think I'm missing a bracket somewhere. Yes, on the end here. Okay, so it started with finding out. Now it's running through the first study it's created from our objective, so I'll come back once this is done. Okay, so you can see now that the optimization routine is finished. And after we fix those few issues, we can now see that the best model is displayed down here at the bottom. It has a accuracy of 0.9, and since the unit we didn't specify any extra parameters to test for it, it just has the model, and it gives you the trial number. And so what I thought about doing is I created another example. Now this example is for if you didn't have access to the ArcGIS Learn. So if you don't have the license for this API, then you can also use the ArcPy image analysis method. So I did start with the ArcGIS Learn because it is easier, as it has the fit and the accuracy routines, which are easy to get the your accuracy assessments from, and just feed that directly to Optuna. And so with this, doing it this way, we have to do some extra processing and some work on our own. So doing it this way, the train deep learning model function, it doesn't actually need any prepared data or anything before it. So we would feed it directly our folder of where the training samples are located, and then it also requires an output folder. So in this case, to set the output folder being different for each trial so that you can go through the trial numbers and link that to the folder, I create a variable called just a counter. And so I want to be able to access I from within our function, so I just made it a global variable. And so what I do is I set the string output folder to just an example folder I have here, and then plus this counter, so it'll be 0. And if I look at my folder right here, I've ran it already, and it created this folder 0 with the files inside it. So if you ever want to use one of these models, then this is a way where you could do that instead of having to rerun the tool again. So after we've set the output folder, you can see a lot of these are going to be very similar from before. And so here, this model does not use Resident 18, only use the Vision Transformer backbone. So I had to create a specific statement for that. And you would do that as well if you had other specific arguments you wanted to pass along to this function for each model. And so if you wanted to just double check that you've entered things correctly and you know all the arguments for each function, you can just select your training files in here, and then you can just select which of the models you want to test. So you can see that this one doesn't accept many arguments, but some other ones like PSP might accept a lot, so you can adjust the pyramid sizes. You can say if you want to use point and render or not. There's various different parameters you can adjust. And so if you want to actually get the accuracy from this method, so you need to collect the result from this. And so we can see what that result sort of looks like down here. So I'm just going to use this string to collect the output message that we're looking for. And so I'm going through each message stored within result. So I have the count of the total amount of messages in there. And then for each one, I'm going to go line by line. And I've printed that below. And I'm looking for the message that starts with this bracket. And so we can see down here, so this part here is where this is printed during training. And then starting here is the start of these messages that I'm printing out. And so it goes through each one printed line by line. And so I'm just looking for the one that starts with this bracket, because this accuracy here is actually the final accuracy from the last epoch. So what I can do is then I can collect this line, and so I've saved that to the string variable. And so what this AST import does is it allows me to convert this, what would be a dictionary, back into a dictionary. So this is right now stored as a string format, but I want it as a dictionary so I can extract this value as a number. So what you can now do is use ast.literalEval. This converts the string into a dictionary, and then I can get the accuracy. So this will return this part here in string form. So this will return, so now the dictionary is a dictionary, but I'm getting the second half here in a string, and I'm gonna set that to be a float. So you can see down below, I've printed that out for you. So it goes from in notation down to the accuracy from the final lane of training here. And so then I'll send this back to Optuna. And so of course, doing it this way, we again only have access to the model arguments and parameters that are exposed for each model here. So for some of these, we have a lot of access to a lot of parameters. Others, we don't have very many, but it still is much more efficient than going through and adjusting everything yourself through the user interface here. So I hope this is helpful to everyone. Let me know if you have any questions or comments. Just remember, you want to set this trials properly and adjust all your settings for whatever type of classification you're working on. So in this case, I've done it for pixel classification, but you could adapt this as well to a similar routine for object detection or even different machine learning workflows within ArcGIS Pro. Thank you very much.